1960 when he was in his prime. And one of the things he is known for is that there's only been one perfect game pitched in the World Series. It was pitched by this gentleman, Don Larson, and Yogi Berra was the catcher for that game. And at the end of that game, he's jumping up, embracing him to congratulate him and celebrate the fact that this has never been done before and it's never been done since. As Carl indicated, Yogi has had lots of profound sayings, and I picked just a few of them to sort of illustrate it. One of them was about baseball. It's 90% mental and the other half is physical. I like this one. He hits from both sides of the plate. He's amphibious. As Carl said, nobody goes there anymore because it's too crowded. And then you'll see more later on, but the last one for now is, I'm not going to buy my kids an encyclopedia, let them walk to school like I did. So Yogi was a very great guy and still is alive, as Carl said. So what I'm going to do today is talk about three projects we're involved with, and a lot of the people who've done the bulk of the work are actually sitting in the room now, having to do with the general topic of nuclear forensics of one kind or another. And then the last is something that Carl actually spurred me on to do a year or so ago when I told him we were going to do an experiment on muon decay in my Nuclear Engineering 102 lab. And he said, well, you know, you can use muons to do a test of special relativity. So I took him up on that, and the whole class in 102 participated in that, and I'll show you a very nice result that we came up with. And the thing which ties them all together is, as the title says, all we're doing is looking. Okay? In each case, we're just observing natural phenomena and seeing what you can learn from that. And the point of this is you can learn a lot. Okay, so the first one has to do with trinitite. And for those of you who don't know, at the end of the Manhattan Project, when the first nuclear weapon was built, it was decided that there were two designs. One of them was more complicated than the other. It involved implosion. And the question was, can you actually make an implosion symmetric enough to get the bomb to actually go off and not fizzle? And so it was decided that design had to be tested before it could be used in warfare. And the first test of such a device was called Trinity. It was done in southern New Mexico, in the desert out there. And actually meant to put a nice picture of a mushroom cloud on this, but you all know what a mushroom cloud looks like. When the explosion goes off, there's an enormous explosion. A lot of dust and dirt and rocks get sucked up from the ground. This particular test was done on a tower, so the device was 100 feet off the ground before it exploded. So a lot of the desert material got sucked up into that very hot, dense material. The dust and dirt got vaporized, and some of the bomb debris ended up getting mixed with that in the mushroom cloud, and some of that material fell down and has been dubbed trinitite. So these are samples of this material that were collected fairly soon after the blast from the Trinity site. They're low-density rocks, basically. They're quite easy to break. They're quite fragile. If you look carefully, you can see little pockets of air that are in here, little bits of different colored materials. So it's a real mixture of junk that got produced as a result of the bomb and all the material being put up into the cloud. It turns out you can buy this stuff from a company down in San Jose, mineralogical research company. It costs about $5 a gram. And if you go to their website, they'll show you photos of all the samples they have for sale, and you can just buy them. You don't need any license, you don't need anything. I ordered them myself. I paid for them with my own money, not the university's money. So I own these. They came to my home via the U.S. Coast Office in unmarked white boxes. They weren't anything radioactive or anything else. I assure you they are radioactive, and I'll show you that in a bit. Not terribly radioactive, but enough for us to do the work I'm going to tell you about. And so the people who are involved in this are Keenan Thomas, Pedro Guillemot, Ross Meyer, George Isabella, who are working with me on this particular project. So what we did was to just take this stuff and stick it in front of a germanium detector, passively to look at the radiation that's being given off. And this is a portion of the gamma ray spectrum. This is the largest sample of 16 grams. We counted for 11 days. And as Yogi said, you can see a lot. So for example, there's a peak over here, which is the right energy to be cesium-137. That's a major fission product. In fact, it's the only fission product that's still present in this material today. There are features over here which can be attributed to two different isotopes of europium-152 and 154. They are not fission products. They're produced presumably by neutron activation of the desert material. There's a peak down here which is attributed to americium-241, and I'll show you in a minute there's some other peaks hiding down there at lower energies. So if you expand the low energy part of the spectrum, here's those lines that I said were from europium, but if you look more carefully, there's a peak here. A peak here at 52 keV and another one at 129, which are characteristic of plutonium-239. And what I didn't say, but I should have at the beginning, is this bomb was made out of plutonium-239. So this is material that did not get fissioned in the explosion, went through the mushroom cloud, incorporated into the trinitite. It's there today. And this americium-241 is presumably not material that was in the bomb. It probably got produced as a result of the explosion as well. Okay, so what? It's sort of neat to see these lines, but so what? So the project that I have Jordan and Ross working on, and Pedro, is to actually use this information to try to figure out the yield of this weapon. Okay? It's a very interesting problem involving chemistry and physics, and some fairly subtle things which I'm not sure I've sorted out yet. I'll show you my answer, but I'm not sure that it's right. And so the idea is there are many assumptions you have to make in order to do this, and I'll show you in a little bit that there are sensitivities at the national labs, as you might imagine, about this kind of stuff. So there are classification issues, and we're doing everything we can to avoid getting into that area. And so the analysis we're going to do is as simple-minded as it possibly can be to sort of avoid those issues. And when we get the wrong answer, I'm going to blame part of it on the fact that we made assumptions that I know must be wrong. So one of the things that we're going to assume is that we have this rock, which, as I've showed you, has both cesium and plutonium in it today. I don't know what fraction of the bomb material, the plutonium that was in the bomb, ended up in the rock, and neither do I know how much of the cesium that was produced through the fissions that happened in that weapon ended up in it. So the simplest thing I can do is assume the same probabilities for those two very different chemical elements to end up there. That's probably a bad assumption, because for one thing, the volatilities of these two materials are very different, and that would certainly affect when they're going to condense out in the cloud. But nevertheless, that's what we're going to do to start with. It'll turn out that should lead to an underestimated weapon yield, because cesium is certainly more volatile than the plutonium, and therefore less of the cesium probably ends up in it than the plutonium. The other thing is the bomb is a complicated object. You can look in Crane's book or anywhere you want to see what a bomb actually looks like. And apart from the main fissionable material in the center, the plutonium, it's surrounded by something they call a tamper. And in this case, it's well known that the tamper was made of something called tubaloy, which for those of you who don't know is natural uranium. So there was uranium surrounding this, and some of the fissions undoubtedly happened there. I'm going to neglect that. And one of the complications is that these objects are extended. You can see they're pretty big. This is a couple inches across. It's probably half an inch thick. We're talking about low energy gamma rays, and so determining the counting efficiency is an issue, especially when you want to take into account the self-attenuation of the gammas getting out of the sample. Okay. So just to show you that we have checked with the authorities, this is a piece of information that I got from Alan Volpe at Lawrence Livermore Lab as to what Lawrence Livermore at least thinks is open information that no one should be worried about saying. So this was plutonium-239 that was used in this weapon. The mass that was in the weapon initially is known. It was 6 kilograms. The yield is also known. It's not that no one knows what the yield is. The yield is known to be the equivalent of 21 kilotons of TNT. It was plutonium-239. As I said, the tamper was this natural uranium material. So talking about those things is not a sensitive issue. Where you get into sensitivities is if you start talking about the design of the weapon. And nothing we're going to do touches on that. And these other things. We're not going to worry about those kind of things. So hopefully we avoid all the questionable things that they would worry about. Okay, so we've counted all those samples. We see the same gamma rays from all of them. They do vary in intensities, indicating that the material did not get homogeneously distributed throughout the trinitite. I wouldn't have expected that. It turns out in this analysis, all you really need to know is the ratio of the cesium to the plutonium in a given sample. The absolute numbers actually don't matter. We've analyzed one sample in detail. We're working on the others, but they give quite similar results. As I said, there's a lot of physics and chemistry that you have to know about in order to get the number. And I'm deliberately not going through the details because I want my students to figure this out. What I get from this one sample I've analyzed so far is a yield of 8.4 kilotons. And I was actually pleasantly surprised it's the right order of magnitude. So even being so simple-minded, you get about the right answer. And the fact that I've neglected all go in the direction of leading to an underestimate. So I think it's actually pretty good. And I would have worried if I came out much closer, because then I think the Livermore folks would have been more upset. I gave this talk a week ago at Livermore, and there were some issues raised, but no one got too upset about this.
Rick, a couple of questions. Did you actually assume the initial mass from, or take it from literature, or do you?
You do have to assume the initial mass. You have to assume six kilograms, correct. If I didn't know that, I couldn't do it. Right. So I use the information that they said is publicly available. Okay, switching gears a bit, another kind of forensics, which has to do with, if God forbid a nuclear weapon went off somewhere in the world, we and other countries would be very, very interested in knowing as much as we could, as fast as we could, about the nature of that. Namely, what kind of material was used, where did it come from, who did it, yada, yada, yada. So a few years ago, a number of our bright undergrads and grad students and postdocs and I did some experiments where we looked at fast neutron-induced fission of things like thorium-232, neptunium-237, and U-238. So we irradiated materials with 14 MeV neutrons, took them out of the beam and stuck them in front of a germanium detector without doing any chemistry or any processing of the material. And what we were able to show in this paper is that you can figure out what the fissioning system was just by looking at the ratios of the gamma rays. And it relies on the fact that the distribution of fission fragments you get depends sensibly on what the isotope was that was fissioning. And so, for example, here, these are three different targets, the thorium, the uranium, and the neptunium. These were taken 18 minutes to 33 minutes after the irradiation was done. And all you have to do is look at the relative sizes of these peaks, and your eye tells you that they're different. We actually did the quantitative analysis, and if you read the paper, there are numbers showing you what these ratios actually are. And here's a similar plot taken 10 to 14 hours later. So the point is, if something like this happened, in my mind, you could simply bring a germanium detector nearby and collect the spectrum, and you could get the information, at least of first order, that you cared about. So that's for fission, but lots of other materials would be irradiated by neutrons if, God forbid, an event like this happened. So, things in this room, for example, or out on the street, would be hit by neutrons. And the idea is that via N-gamma, NP, N-alpha, N2N reactions, and so on, you'll make radioactive nuclei that could also be measured. And it turns out, as you might expect, the threshold energies for inducing these reactions are different. And so by looking at the relative yields of these different products you get as a function of neutron energy in the laboratory, then if you went and measured such a thing in the field, you could sort of figure out roughly at least what was the energy of the neutron that caused this to happen. And you might say, well, who cares? But the point is that if it's a fission weapon, you get one spectrum of neutrons. If it's a fusion weapon, you get much higher energy neutrons. And people would be very interested in knowing if fusion or fission had happened in a given event. So that's why folks are interested in this. The way we do this is, again, to irradiate the materials with neutrons. We actually go up the hill to LBL's 88-inch cyclotron, which you wouldn't think of as a good place to make neutrons, but in fact it is. You take a deuteron beam and you slam it into a thick beryllium target, and the deuteron, as you know, is just a weakly bound system where proton and neutron. It doesn't take much to separate them. The proton stops in the target, and the neutron keeps on going pretty much like nothing happened. So you end up with not exactly a monoenergetic neutron, but you get a neutron that has roughly half the energy of the beam of deuterons you sent in. So we get 3 MeV, and I say, sort of in quotes, because it isn't monoenergetic as a spectrum, but we use this to mimic a fission neutron energy spectrum. And then we raise the beam energy, so that's at 6 MeV, and that produces 3 MeV neutrons. You raise the beam energy to about 30 MeV, and that produces something like 14 MeV neutrons. And we irradiate a bunch of different targets, and then we look at what happens. So we did a test run a while ago, and I'm just going to show you one or two examples of how this works. So this was an aluminum target that was irradiated with 3 and 14 MeV neutrons. So you irradiate, I think, for a minute. You pull the samples out, and you count. This is the first 10 minutes of observation after the irradiation. You can see lines which are characteristic of magnesium-27, aluminum-28, and sodium-24. The aluminum-28 comes from neutron capture on the one stable aluminum isotope. The magnesium-27 is from an NP reaction on the aluminum, and the sodium-24 is from an N-alpha reaction. So you then raise the beam energy to 30 MeV, which makes our 14 MeV neutrons, and you see the same pattern of gamma ray peaks, but the intensity ratios are quite different. In particular, the sodium-24 has come up a lot here relative to the others. And the way we do this analysis is, these are the energies of those gamma rays. This is the reaction that is responsible for making them. Here are the reactions and their laboratory thresholds. So for an N-gamma reaction where you're just capturing a neutron, there's obviously no threshold. So we take that as our standard and we normalize everything to that, because it doesn't matter in first order what the neutron energy is. The NP reaction has almost a 2 MeV threshold, and the N-alpha has a 3.5 MeV threshold. So now you look at, here's the 3 MeV irradiation. We take the N-gamma peak and we just normalize and call that 1. With respect to that, the NP reactions have these strengths, and the N-alpha reactions have these strengths. When we raise the beam energy, or the neutron energy to 14 MeV, the thing I'd like you to pick up on is how much the N-alpha goes up. It jumps up enormously, and it's actually bigger than the N-gamma reaction there. And that's because now we're way above this threshold energy, and it's a lot more probable for the N-alpha reaction to occur. So just by looking at that ratio, you could tell the difference in neutron energy. We didn't do it just for aluminum. Here are a couple other targets that we looked at. This is gallium, and if someone asks why we picked gallium, I'll be happy to tell you later. Again, different reactions that can happen on the 2 different gallium isotopes. Again, we take the N-gamma reaction as the standard, call that gamma ray intensity 1, and relative to that, the N2N, which is the major way this gamma ray gets produced, is very small at low energies and jumps up enormously when you go to higher energies. And the point is, again, simply by looking at the ratios of the relative intensities of these peaks, you can figure out what neutron energy roughly must have been responsible for producing them. There are a lot more elements that folks are interested in. We're working very closely with folks at Livermore to pick the particular targets that they are interested in. We just got done purchasing 25 different materials. We've got nice metallic foils of almost all of them, and we've got beam time promised up at LBL for the next month or two, where we'll be irradiating all of these with different energy neutrons and then measuring the gamma rays that come off to figure out where we can spot differences easily for these different materials. Okay. Let me jump back in history a little bit and talk about Chernobyl for a few minutes. So in 1986, when Chernobyl happened, I was working up at LBL, and we were sitting around the lunch table one day, right after it happened, and wondering whether we might be able to see Chernobyl fall out of Berkeley. And this was roughly a week after the event. And I went home that night, and it turned out it was raining. And so I took a bucket and I stuck it under a downspout coming off my roof and collected a liter of water and brought it into the lab next day and stuck it in front of a germanium detector. And this is what I saw. Very characteristic peak at 364 keV, which is from iodine-131, a major fission product. And just to make sure that I hadn't screwed up, we also counted some tap water, and there was nothing there. So I reported this right away to the folks at EH&S at LBL, and they said I must be nuts because they had done the same thing and hadn't seen anything. So we switched samples and talked about how you actually do statistical analyses of things, and eventually they agreed, and very soon after that, everybody all over the world was seeing Chernobyl fall out. But this was one of the first reports that I know of, at least. One of my colleagues at LBL in those days was a gentleman named Bernard Harvey, a very famous nuclear chemist, who was spending his summers in France. And after Chernobyl, all of his neighbors were very concerned about the food they were consuming and how much of it was contaminated with fallout from Chernobyl. So Bernard came back and talked to me about it, and we decided to spend the next summer purchasing as many imported food products that were being sold in the San Francisco Bay Area as we could and examining them for evidence of Chernobyl fallout. So this is a photo of some of them, which I still have downstairs in my lab. This is some powdered milk, this is pasta, this is thyme, and of course some beer. And the reason these stuck around and didn't get consumed is they all have Chernobyl fallout in them, and you can still see it today. This is the sort of thing we did. This is from an LBL report we wrote back in 1988. This is a spectrum. This happened to be Norwegian goat cheese that we bought at one of the local cheese shops. And again, no processing, no nothing. You take the block of cheese and stick it in front of a germanium detector, and this is what we saw. Characteristic gamma rays from cesium-134 and 137. And again, just as a control, we got some good old American cheddar cheese and didn't see anything. So this really was stuff that came from Chernobyl. And if you ask, well, how do you know it was from Chernobyl and not some other event? It turns out the ratio of these peaks is a measure of how long the fuel was in the core of the reactor. And it's known from the initial fallout that fell in Europe what that ratio was. And we were doing this roughly a year later, so you actually have to correct for the decay of the 134, but when you do that appropriately, the ratio we infer is the same as what was seen initially. So this stuff really did come from Chernobyl. The levels are incredibly low. I don't mean to be alarmist, and we did try to publish this stuff and it got rejected, partly because people said we were being alarmist. These are the levels we actually saw. We counted, I don't know, 35 or something different samples of various materials from different countries. In about 2/3 of the samples, we didn't see anything. In 1/3 of them, we did see something. The units here are picocuries per gram, very, very low levels, but nevertheless way above our sensitivities. Mushrooms were particularly noticeable. Here's the beer, even though it's mainly water, nevertheless, material got into the hops and the grains that went into making the beer, and some of it ended up in the beer. Feta cheese, goat cheese from Norway was the highest thing we saw. Okay, so that was actually kind of fun. But as Yogi said, it's like deja vu all over again, because a few years ago we had another nuclear accident, Fukushima, and it turned out it was raining here right after Fukushima. And so the same thought process came through my head, well, we did it once before, let's try it again. So Perry Chodash and Chris Angel and I went out and collected rainwater for a week. Kai and his group are still doing these kind of measurements and looking for evidence and actually seeing evidence for Fukushima fallout now in local rainwater. And this is a paper that we published in an interesting journal called Public Library of Science 1. It's a free online journal, so you don't need a subscription. Anyone in the world can get full access to this thing. And also they run a blog with each paper so people can comment on it. It's actually sort of interesting. So these were the results we saw for a whole bunch of different fission products that we observed in the rainwater. Again, nothing too surprising in terms of the isotopic composition. The quantitative numbers we get, I think, agree very well with the stuff Kai's group got, and also with what Al Smith and company got up at LBL. I don't think there's much controversy about this. What was a little surprising is the following summer, Boris Lowe and Chris Rozek and I were doing some measurements of background radiation all over the San Francisco Bay Area. And so one day we took our germanium detector outside on the Berkeley campus. You might know this is Boris Lowe, and this is Northgate right here. And if you take the detector and sit it on top of that little grassy mound, this is what you see. Most of what you see are peaks from the natural background radiation. But right here and right here and right here are those same cesium-134 and 137 lines. This is Fukushima fallout, which came down in the rain, got into the ground, and incorporated into plants. Okay, and it's basically there forever now. And if you take the detector outside, you can find it quite easily. There was an open house up at LBL a couple of years ago where we set up a germanium detector, in fact this one in the parking lot outside the cafeteria, and turned it on to show people what the natural background spectrum would look like. And to our surprise, we saw the Fukushima fallout sitting there in the parking lot. Okay, so there's been a lot of misinformation, I would say, in the popular press and online having to do with how bad the Fukushima fallout situation is with regard to folks in the US. During the summer, a bunch of these things showed up online, and I've just copied a few of them, attributing to Fukushima incidents of birth defects in children born in the United States. People talk about it being suicidal for a person to travel to Hawaii these days because of Fukushima fallout. I mean, this stuff is total nonsense. But it got to the point where I got a phone call in my office one day from Reuters News Service asking my opinion about this. And what I ended up saying got quoted on the nightly news. And what I said was, you know, things can be quite bad in Japan. However, it's a long way from here to Japan, and there's a lot of water in the Pacific Ocean. And so what I said was, basically, no matter what happens over there, nothing terrible is going to happen in the United States. And that got picked up and quoted, and I got some responses from that. So I got an email. The first part I don't mind so much, but then the rest of it is actually pretty nasty. And so I decided I had to do something about this. And my son, who watches these things as well, suggested I start looking at food products being sold here now that might have Fukushima fallout in it, and in particular fish. So obviously there are fish swimming around the Pacific Ocean. Some of them actually migrate pretty far, some of them stay close to shore. And it's true, we all know that Fukushima is leaking lots of radioactive material into the Pacific Ocean. And there have been some reports already that people have seen Fukushima fallout in fish. And I wanted to see, well, what's in the stuff you and I go to the fish market and buy and eat? So we did that. Before I delved into that, back in 2011, a month after Fukushima happened, because of all the rain, the weeds in my backyard were growing like crazy. And I went out there and pulled up a few handfuls of these weeds and brought them into the lab. And I've kept them. And this happens to be 30 grams of the material that we still have today. And 2 weeks ago, Pedro and Keenan and I stuck it in front of a germanium detector, and this is what you see. Okay, again, these are natural background lines over here, but this peak and this peak are 134 cesium, and that's 137 cesium. So within a month, this material had come across the Pacific, fallen out in the rain, ended up in the soil, and these plants grew and contained it. And back in those days, I wondered whether it was just sitting on the surface from the rain or whether it had actually been incorporated into the plant. So I made wheat soup. I took this stuff and I boiled the heck out of it. I counted the liquid. There was nothing in it. It's all in the plant. This is really bare in the plant. Okay, the level that we see, and I'll come back to this in a little bit, it's about 15 becquerels per kilogram. So 15 decays per second per kilogram of material. And in this case, the material I'm talking about is the weeds. Okay, so what we then did is I went to the local fish markets and I bought fish from all over the Pacific, took it home. So I bought roughly a pound of each material and then took it home and cooked the heck out of it on my barbecue outside so I wouldn't stink up the house. So this is about a pound of Philippine tuna, and this is about a pound of Alaskan cod. We have a bunch of different samples. I cooked them to reduce the volume so we could count them to higher efficiency. Essentially all you're doing is boiling off the water. So the mass that we ended up with is roughly half the mass you started with. This is 440 grams of that Philippine tuna, counted for about 2 or 3 days. And although the peaks are not as impressive as they were before, they're still in the right place. This peak right here is 137 cesium, and even though you may not believe it, that and that are also the peaks from cesium 134. We've counted a bunch of different samples, and in roughly half of them we can see the fallout, and in the other half we don't see anything. We've also counted some yogurt, and there are a couple more samples yet to be done. The levels that we see are all less than half a becquerel per kilogram. Okay, again, this is Fukushima fallout now in the fish. What's interesting is we can also measure how much potassium-40 is in the fish. And the potassium-40 activity is 200 becquerels per kilogram. Okay, people worry a lot about this and no one even knows about this. Okay, it's orders of magnitude more. It's there all the time. We're eating it, we're ingesting it, our bodies are full of it. Okay. What does the FDA say about all this? So the FDA, of course, knows about this, and they've established limits for various types of radioactive materials in food, and they're also very concerned about milk for obvious reasons. It turns out that for cesium-134 and 137 combined, the FDA limit in these same units is 1,200. 1,200 becquerels per kilogram is what's allowed, and we're seeing less than half. Okay. The problem, if you like, is we have ridiculously sensitive detectors. I mean, our detectors can see things which are not a health problem to anybody, but we see them, and then you have to sort of explain to people what does it really mean. And the bottom line is this is not a health hazard to anybody, in my opinion, and I think in anybody else's opinion. We're a factor of 2,000 below the FDA. So if this stuff hadn't rotted already, I would have been very happy. Okay, so I'm going to come to the final topic, and this will take a little longer, and I have to thank Carl and the whole NE 102 class for this. This has to do with another kind of observation, and it's not with forensics. This is a test of a very fundamental idea in physics, namely relativistic time dilation. And we use cosmic ray muons in order to do this. So the idea is that at the top of our atmosphere, protons mainly are coming in from outer space, cosmic ray protons. They're interacting with nitrogen and oxygen near the top of the atmosphere. And these are GeV on up kind of energies. So very high energy reactions are happening. Pions get produced, both pi plus and pi minus. They are very short-lived particles and they rapidly decay into muons and various kinds of neutrinos. You know I like neutrinos, but I'm not going to talk about them today, I promise. What we're interested in are the muons that get produced. And the muons themselves are basically heavy cousins of electrons. in the laboratory, when they're sitting at rest, they have a lifetime, of 2 microseconds. So they decay very quickly into positrons and electrons. So this is all going up at the top of the atmosphere. The mean muon energy at the top of the atmosphere is about 6 GeV. They travel down through kilometers of air. By the time they get to the surface, the mean energy is about 4 GeV. And these high energy muons are what we call minimum ionizing particles, which means as they're traveling through material and ionizing it, they lose as little energy as actually possible, and that turns out to be 2 MeV per gram per centimeter squared of material they traverse. We make use of that later on. Okay, so in our lab downstairs, and you're all welcome to come down to 1110A sometime and see that, we purchased a large tank of liquid scintillator. It's a cubic foot of liquid scintillator in a steel tank with a single phototube staring in to look at the scintillation light produced when things happen inside. And so what I'm illustrating over here is muons traveling through the detector. So even though we're in the basement, with 6 stories of building on top of us, most of the muons that come through keep on going. And so they go through our tank and lose a little bit of energy, but don't actually stop there. And depending upon the angle with which they go through, they traverse different amounts of material and hence will produce different energy losses. And what's being shown here is an energy spectrum of these through-going muons. So this is the energy the muon deposited, this is the number of events, and if they went vertically through, we would expect to see a peak at 2 MeV per gram per centimeter squared times about 30 centimeters. The density of this stuff is a little bit less than 1, so we'd expect a peak a little bit less than 60 MeV, and that's what this bump is. So these are muons that just went straight through. The ones down lower are ones like this one over here that sort of clipped the corner and didn't travel through as much material. The ones that are higher energy are the ones that made a longer than average trajectory through the tank. So this is what through-going muons look like. What we're interested in for this experiment, though, is muons that happen to decay. So in the second part of the experiment in this lab, the students look for events where something came in, and then a little bit later, there was another flash of light, which is indicative of the muon decay. That's quite a bit rarer process, and so to get a spectrum like this, well, this one's a long one, but it takes a few hours to get a decent looking spectrum. To get the spectrum I'm going to show you in a few minutes takes more like a week, because very few of the muons will actually stop. So the way we do the experiment, and this is an interesting little bit of electronics, which the students and I always have a little trouble with, you're looking for 2 events in one detector. Normally, if you've done coincidence experiments, you have 2 detectors, and you look at an event where one fires, then a little bit later or before the second one fires. It's a little more difficult to look for 2 events from one detector, but this is the way you actually do it. We did this again in as simple-minded a way as you possibly could, after having gone through it a year before in a very complicated way, which I didn't like and the students had a lot of trouble with. So the signal from the phototube comes out here, you split the signal, and somewhat counterintuitively, you delay the signal to the started or time to amplitude converter. You take the direct one, you put it to the stop, and you measure the spectrum of events that come out. This is a device which measures the difference in time between the arrival of that signal, and it produces a voltage which is proportional to that time difference. And from that, you can measure the muon lifetime. So this is data that our students in 102 actually took. You measure the number of events you see as a function of time after the start comes in, and you see a beautiful exponential decay curve. The experimental fit to this data gives 2.0 microseconds. The accepted value is 2.2 microseconds. And even that discrepancy we understand. It's kind of an artifact of the way the experiment's done. It has to do with the fact that not all the muons actually decay. Some of them are captured in the material and don't produce a signal that we see. But the point of this is that when a muon stops, the lifetime is 2 microseconds. Okay? So now we want to make use of that, and now we're trying to measure what happens when muons are traveling at relativistic velocities. Do they still decay with that kind of lifetime, or does relativity play a role? And the reason relativity should play a role is because of Mr. Einstein time dilation. That when things are moving fast compared to the speed of light, instead of just computing time as distance divided by velocity, you have to include this gamma factor here. 1 over 1, the square root of 1 minus v squared over c squared. Essentially, moving clocks that are moving rapidly compared to us appear slow. And the muon is a clock, okay? When it's sitting at rest, it lives 2 microseconds. But as a cosmic ray, it's traveling very near the speed of light, and therefore it should run more slowly. That means its decay rate should be slow. And if you think about it for a minute, well, I'll get to that in a second. Okay, so first of all, you have to know how fast these muons are going. So we did that too. We went down to 1140, where there's this nice big scaffold, and we took our detector, and there's one detector sitting over here. This is Boris Low to give you a sense of scale again. There's another detector over here, and we measured the time of arrival of a muon that came here relative to that. So the time it took the muon to get from here to here. And then we moved this detector up to here, and then we moved it up to here. And you measure the time difference, and since you know the distance, you know the velocity. So these are time spectra, if you like. This is when the two detectors are sitting next to each other on the ground. This is our reference. When the detector is now 6 meters away, the peak shifts over, indicating it took some time for the muon to travel from here down to here. And that time difference allows you to figure out the velocity. We're not claiming to have done this with terribly great precision, but we find that it's consistent with moving at just a little bit less than the speed of light, which is what we knew had to happen. Okay. Well, the idea now is that if muons really had a 2 microsecond lifetime, regardless of how fast they were moving, then very few of them could make it from 10 kilometers up in the atmosphere to the ground. Because if you think about it, the fastest a particle can move is the speed of light. And the speed of light in units that are sort of handy is a nanosecond per foot. So if the muon lives 2 microseconds, that's 2,000 nanoseconds. The furthest it should go before it decays is a few times that. It should only go a few thousand feet before it decays. And yet they're coming from 10 kilometers. So the only way they can get here is because of relativity. So how did we do this? We had a plastic scintillator that we could take outside with a portable data acquisition system. This is Jordan Sabella out here on the Berkeley campus. We actually took this thing up to the top of Mount Diablo, and we measured the flux 4,000 feet above sea level, and then at several elevations as we came back down. This is the class up on the top of Diablo. We took it down to the Berkeley Pier to get a measurement at sea level, and you measure the flux as a function of elevation. If the muon were not experiencing relativistic time dilation, you'd expect to see this curve in blue. These are the data points that you actually observed, that we measured, and the red line is what you expect from special relativity. So no big surprise, Einstein was right, but this I think is a very nice demonstration of it. And I was a little surprised at how big an effect it is. It's not a little effect. This is like a factor of 5 we're talking about in the difference in flux you expect with no time dilation versus what you're going to see. And these are almost all undergraduates who did this stuff, so it's kind of fun. And I thank Carl for suggesting it. Okay, so I've gone through the examples I said I was going to do. The point of all this is, as I said, by looking you can see a lot. There are a lot more experiments of this type that we've done and we plan to do in the future. I haven't had time to go into them. If there are questions, I can talk a little bit more about it. But I'll stop here with another one of Yogi's famous sayings. Thank you.
I knew you would not disappoint. I have questions, but let's start from the audience here.
Why'd you use gallium?
Pardon?
Why gallium?
Why gallium? Oh, so it turns out in a plutonium weapon, they actually alloy the plutonium with gallium to make it stable. So that's why we did it. People are interested in that. Okay.
How do you come up with neat experiments like this?
I'll tell you part of it, and it has to do with something I told my graduate students. When I got hired as a postdoc right out of graduate school, I went to the University of Washington. And in those days, at least, they did not hire people into particular research groups. There was a laboratory. They hired you to work in the lab. And what they told me when I got there was to go around and talk to all the different faculty members, see what they were up to, and figure out where I would fit in. So I did exactly what they told me to do. I went and talked to everybody. They were all extremely nice. And they explained to me in gory detail what they were doing. But to a person, they all said, you know, we actually have enough people to do what we want to do. We don't really need you. And this was really shocking to me. And I went back to my office and I thought, God, what am I going to do? I'm a postdoc, fresh out of graduate school. I know I have to produce experiments. I know I have to produce papers. What am I going to do? So it forced me to think a lot. And I was able to think of experiments that it turns out I could do on my own, thanks to all the equipment that the laboratory made available to me. So in the first year, I published 2 single-author papers based on that. And it began to get noticed around the lab, and a bunch of graduate students who were actually working on PhD theses with other people came to me and said, can I help you on some of your experiments? And so there were 3 or 4 graduate students, including Kevin Lesko, you probably know, who worked with me. And over the course of the next couple of years, we published tons of papers that they all have their names on. And it really helped establish me and got me into thinking about simple things I can do. And I don't mean to say the only experiments I do are simple, but my attitude always is you start as simple as you possibly can. And if you can't see the effect you're looking for, then you make it more complicated. I know a lot of people actually start the other way. And I won't say any more about that.
How do you think the Americium-241 gets there? Is it multiple neutron capture?
That's my guess.
But you don't see any 240.
That doesn't produce very many gamma rays that you can see. And I've forgotten what the gamma rays are and what the intensities are. But the americium, for one thing, the 241 is relatively short-lived. It's got big gamma range. So I think it's from multiple neutron captures. I can't prove that. There probably was some americium in the plutonium. It depends on how long the material was in the reactor, and that I think is a piece of classified information. I don't really want to go there. I don't need it for this analysis.
So, let me ask a question. When I suggested this to Rick about the time dilation experiment, it was because when I was a student at MIT had made a series of little films, which at that time were on these little 8mm cassettes. Really old stuff. And a number of MIT faculty made 15 or 20-minute videos, which were kind of pretty. And David Frisch, who was a high-energy physicist, whose son, he actually taught the junior lab. His son actually was a high-energy physicist in Chicago.
Henry Frisch. I took classical mechanics from him.
Yeah. But the thing that surprised me about this measurement, and when I thought about what you were doing, I always thought that it would be kind of the weak point or a problematic point. So you first measure the velocity spectrum muon going through.
Right.
I would expect that, yes, there might be a mean, but it would be a very broad distribution.
Absolutely.
But of course, now the dilation effect, the 1 over 1 minus beta squared, is going to be all over the map with relatively modest changes of velocity. How did that model fit come out so nicely? I would have thought that would have been a problem.
So what we did, and you're quite right, you are sensitive to what value of gamma you take to do that calculation. So to do that calculation, we took the 4GeV as the real energy, and therefore we calculated gamma based on that. You're absolutely right, there should be a distribution, but we took that, and that's what that fit is. Right, Jordan?
Yeah.
Okay, Jordan actually made a fit.
And having done that, it just came out really nicely.
Yeah, that's right. We didn't fudge.
Okay.
We didn't fudge.
Okay.
And our velocity measurement is consistent with that energy. Obviously, the velocity measurement has a big error bar on it, because we couldn't get the detectors very far apart. But it's certainly consistent with that energy.
Other question I had. I was stunned. I mean, you're working with the people at Livermore when you're looking at the 3 MeV versus 14 MeV
Right.
activation.
Right.
Who are, these are the experts. They're paid to do this forensics business. I mean, a very large budget nationally goes into
Right.
this. How could we not have known?
It was a shock to me too. I said it must all be known. And it turns out what's known is the fission yields. You go to the England and Ryder tables, it tells you the yield of every single isotope. And then you go to the table of radioactive isotopes, and it tells you the half-lives and the gamma ray intensities. So in principle, you can put those two things together and calculate what the spectrum should look like. We actually did that.
Yeah.
Okay? And it turns out there are enormous discrepancies in some cases that you care about. And my guess is it's in the fission yields. They're not actually known terribly well. And we pointed that out in both of our papers.
But the fundamental cross-sections that you're measuring were not in the nuclear data, the National Nuclear Database? Or?
So we were not measuring any cross-sections.
Okay.
These are all ratios of gamma ray intensity.
Simply ratios.
Simply ratios.
Okay.
Because the idea was, we wouldn't know what neutron flux things saw, and we don't actually care about that for this particular problem. So we're just looking at the ratios, and that depends on the fission yields and the gamma ray branching ratios and half-lives. That's about it.
Okay. Further questions? Absolutely do. Well, Rick, thanks so much.
I finished early. I'm keeping with the baseball theme. The A's won today, 6-3.
All right. Wow.
Go A's. Thank you.
Oh, well.
I should have done
The fishing wheel is utilized.
So, great. See you. How are you? Great.